All right. So today, our plan is to start talking about hypothesis testing, and this week, hopefully, we're going to finish chapter 9. And according to schedule, we seem to be 1 week behind the schedule, but uh, the chapter 11, we are probably just going to finish the entire chapter in 1 hour or so. So it's just one section, the least squares estimation, which is very simple to describe, and it says just one equation. We are going to see it's a really simple topic. So this is not going to actually take the whole week. So we are going to skip some of these, and we may. So therefore, we are going to probably have some of chapter 6, borrowing some hours from this week's topic. So right now we are at week 10, so we should have started chapter 10, but let's see, maybe we'll start chapter 10 this week at the second hour on Thursday. But yeah, chapter 9.4, we're going to see hypothesis testing. We are going to learn some errors that we may make when we're doing statistics, when we make our samples may contain certain errors. Sampling error is something that is not avoidable. We cannot be 100% certain all the time. So there are accuracy levels, and we are going to talk about those. And the level out, we are going to talk about level alpha hypothesis testing, which is the same alpha that we used in confidence interval. We are going to see. Okay, and we are going to see the concept of p-value. This is the topic for this week. These are the topics for this week. And yeah, and for the rest of the semester, we are going to see one section from chapter 10, one section from chapter 11, sections 5.2 and 5.3 from not the entire 5.3, so a couple of sections from chapter 5, and again the entire chapter 6. So this is the plan until the rest of the semester. And your third assignment will be a written assignment, which is going to be about this entire chapter 9, hypothesis testing. And your final assignment is going to be a programming assignment, which you'll be writing some simple MATLAB Octave online code to simulate random variables that are coming from certain distributions, and how simulation can be used to compute probabilities that are difficult to compute analytically. So we are going to talk about those in chapter 5, and your final assignment, which is that small programming assignment, no more than 40 lines of coding. You will be that will be your, yeah, that's the Monte Carlo chapter. Chapter 5 is the Monte Carlo chapter. You're going to be conducting Monte Carlo simulations in your last final assignment. So let's go ahead and start hypothesis testing. So right up to this point, we have built confidence intervals for population means, population proportions. So when we want to estimate something, we have a population, for example, we take a sample, and we just say that with certain confidence, for example, with 95% confidence, my actual population mean is in this interval. So this is what we did in confidence intervals. Now we are going to, in hypothesis testing, this population usually is the normal expected thing. And here in hypothesis testing, we are going to be testing some hypotheses against this normal population. Okay, so for example, let me start hypothesis testing with a simple example, which says, for example, the internet connection speed is now, for example, your internet service provider may claim that your internet connection speed is now, after an upgrade, should be more than 20 megabits, okay, per second. So 20 megabits per second, if you want, and your internet service provider is claiming that it's larger than this, okay? So after the upgrade, now it's more than 20 megabits per second. Now, in order to, so this is the hypothesis. So here, when we say when we say more than 20 megabits per second, we just, for example, we will not treat this one 0.20.0001 as significantly more than 20. So here the hypothesis that we're going to build is that, so the internet service provider is claiming that it's more than 20 megabits per second. We'll build our hypothesis thinking that with the equality, all hypotheses, the normal case, which is against our which is called the null hypothesis, is usually is always an equality. So we are going to take a sample, and we are going to say that the mean of this sample is 20 megabit per second. Okay, so this is our null hypothesis, claiming that no, it's something in the normal case it will be 20 megabits per second, but the internet service provider is now claiming that it's actually not this, it's more than that. In order to in order to reject the null hypothesis in favor of the alternative hypothesis, which is going to be saying that no, actually this is what the internet service provider is claiming, it's more than 20 megabits per second. So these alternative hypotheses can be inequalities. In this case, for example, I'm giving an example which is called a one-tailed t-test, z-test, for example, depending on how many samples we're going to take. But it's a one-tail hypothesis test in which we will be looking for, we will be collecting a sample, and we will be converting the sample average into a standardized z-value if we have large number of samples, and if you know the standard deviation of these internet connection speeds, for example, we will be conducting the z-test. Or if the sample size is large, again, and even if we don't know the standard deviation of the population, we will be using the standard deviation of the sample. Again, we are going to conduct what is called the z-test. But this is not this z is not different than standardizing your expected value of x bar, which was actually mu, and the standard deviation of x bar, which is your standard error. So here we are going to compute the z. No, our population mean, so this is a very good question. So what is the population mean in this case? Because if the internet service provider claims that the internet service speed is now greater than 20 megabits per second, if your population is that new internet speeds, then we cannot use this mu as the population mean, right? So this is a very good question. But here, when we're conducting hypothesis test, our population is actually the population for the null distribution. Okay, so the null distribution is based on some assumption which says that mu is 20 megabits per second. So that's our assumption. So if this is the assumption, the population for the null distribution, this is really important. We are looking, our population in this case is the population for the null distribution, for the normal case. So it's going to be, for example, a normal distribution centered exactly at 20 megabits per second. So this is the new population after the upgrade. May be different, but we're not going to be making claims about the new population. The null distribution is the distribution of the null distribution that we draw here is the population that is based on our null hypothesis, which is it's equal to 20 megabits per second. In the normal case, it is this. So when we collect the new sample, if we see that the new sample's average x bar is somewhere here, for example, it's going to be a significant enough evidence that, oh, it's really indeed not 20 megabits per second. It's significantly larger than that. If it falls here, if x bar falls here, we will still claim that no, maybe it may still be, I mean, it's larger. The x bar is, if x bar, as I said, is 20.0001, In this case, mathematically, it's larger, but we're not looking for that. It can still be, if it's 20,001, if I get a different sample, it means that it can be less than that. So in order to accept the alternative hypothesis in favor of the null hypothesis, we need really significant evidence to do that. Okay, so this is therefore the level alpha test that we are going to see, the level alpha z test. For example, when alpha is equal to 0.05, which means that we accept to make 0.04 errors with 0.05 probability. When it's a right tail test like this, we are going to have an acceptance regions for accept. So this region to the left hand side, which contains 95% of the null distribution. This is the distribution for the null hypothesis. This is going to be the acceptance region, and this is going to be the rejection region. So in order to, which basically tells us that we will be accepting the alternative hypothesis that is really indeed greater than 20 megabits per second now, only if the z value that we compute here is greater than this threshold. Okay, so this is one. Another example is, for example, if you want to, in a legal case, for example, you want to convict. The jury has to convict somebody, right? For example, by default, the assumption is that the defendant is not guilty. So if there is only significant evidence against that he is not guilty, then we are going to claim that he is guilty. So the normal case is he is not guilty, and if the distribution is going to represent the people, the distribution of people who are not guilty. So it's the normal case. Only if we have significant evidence. Just a small single evidence, which may be also observed in some of the normal population who are not guilty, will not make this person guilty. In order to deem that this person is guilty, we need significant evidence. So that's again, that will be our alternative hypothesis. And in order to accept alternative hypothesis in favor of and reject the null hypothesis, we need to have significant evidence that shows that. Okay, so here, as I said, in this case, the null hypothesis, the normal case, is always an equality, and the population here, the population we think about here, is not is the case that corresponds to this normal case where we assume that mu is 20 megabits per second. Yeah, and the number of samples is also important because, as you can see, when we conduct this z value, if the number of samples is small, the standard error is going to be large. So in that case, when the standard error is large, you will not, your evidence, for example, if you have found something here like this, but if you have small number of samples, since you divide, you also take into account the standard error, which takes into account the sample size. Okay, so the standard error of x bar here, if you know the standard deviation of x, okay, it's the standard deviation of x divided by square root of n, right? So if the sample size is small here, this is going to be larger than the standard deviation of x bar. So therefore, the sample size is inherently taken into account in this standard error formula. So that also tells us whether you have a significant evidence or not. The x bar, the value of x bar is important. How different it is from the mean. How different x bar is from the mean, and what is the sampling error? What is this? What is your the error you're going to get here for x bar? What is the potential error you can get from x bar, which is given by this? Oh, by the way, last time when you asked why we divide this by square root of n, I actually did not show you the derivation of the formula correctly. So it's the mistake that I was making here is that when I have this x1 plus x2 plus plus x3 and all the way to xn, uh, I just wrote this as n times x, right? I have n x's. This is incorrect. I cannot do that because these are all individual random variables. And all the summation of those individual random variables is not the same as getting a single random variable and multiplying it by n. This is the, I mean, in terms of the random variable, the summation, this may be the expected value of the sum. I mean, this is not even the expected value. I mean, it's n times the expected value of xi. So this was my mistake. I thought that the summation of this was n in the beginning, and then it was then n square sigma square. Then if you divide it also by n square, oh, you get the, I mean, this is the part that I was confused. And this is the part that is not correct. So the when you add the, again, the linearity of expectation, the variance of the sum, the variance of the sum is equal to the variance of these individual things because of linearity. In other words, the variance of sum is actually equal to sigma square plus sigma square plus sigma square plus sigma square. You have n of those, right? So therefore, when you have n of those sigma squares, so these are individual random variables. So the variance of individual random variables is the summation of their variances. Therefore, the variance of the sum is actually, there are n of those, n times sigma square is the variance of the sum. Now, if the variance of the sum is this, what about the variance of sum divided by n, which is our average, right? So this is our average. The variance of sum divided by n, so this was the variance of sum, is equal to, so this is now our constant, it's equal to 1 over n square of the variance of the sum, which is n times sigma square. These n's cancel, which gives us sigma square divided by n. So this is the variance of the average. If the variance of the average is this, the standard deviation of the average will be the square root of this thing, which is sigma divided by square root of n. So this is how the formula is derived. Okay, so we have this, if this is the standard deviation of x, some random variable, the average of n x's is the standard deviation is going to be this. So this is the correct deviation derivation that you do. So why did we write 1 over n squared in the last line? Because this sum is a random variable. So the variance of na, some random variable, or we may like it like this, the variance of ax, where a is a constant here, is equal to a square variance of x. So again, it's the again in that table that shows linearity of expectation parameters. So since it's now this is our constant. My previous error was treating all these summation of different independent random variables as a single random variable multiplied by n. This is incorrect. So this first line is very critical. That was the error that I was making, which canceled out everything. Then the standard deviation of x bar then is equal to sigma as well, which is not correct. So this is not, these are individual random variables. In order to write the variance, so you should take a look at what is the variance of x plus y. Okay, variance of x plus y, if you remember, is equal to the variance of x plus variance of y. So therefore, we need to, so the and variance of x is sigma square, variance of the other x's. These are all different random variables selected, sampled from the distribution. So it's you should add actually n sigma squares. So therefore, the variance of the sum comes as n sigma square from here, and when you divide it by a constant 1 over n, now the variance of that average becomes 1 over n squared times the variance of that sum, which was we found as n times sigma squared. This is how we get this derivation. Okay, so yeah, so therefore the sample size, in terms of significance, the sample size is included here in this computation of the standard error. If you have a small sample, which means that the standard error is going to be large, larger than the one with a large sample size. When this is large, your z-value is going to be small and you will be in the acceptance region. Now, let's go step by step. The S square, okay, here in S square, all good question. The S square is the case where we don't know if the population, in this case, for example, we are just given the mu, but in certain cases, we may also, I mean, this is just the null hypothesis, just state that the mean connection speed is 20 megabits per second. But if in the question we are not given that, the standard deviation of connection speeds, the standard deviation of the population is not given to us in the question, then we compute it by estimating it from the sample that we collect. So when we have a large sample here, the difference is the same. So here, let's take a look at this one. So this is, we can compute this only if the sigma, which is the standard deviation of those connection speeds of the population, is given to us. If the sigma is not known, we would not be able to compute the standard error like this. So what do? We compute the standard error by the sample standard deviation. So how do we compute the sample standard deviation? So the sample standard deviation is, we collect a sample, okay, which contains again n individual n random variables. So this is our sample of size n. So the sample standard variance of this is called S square. So the sample standard so if you find this S square of x, how are you going to do that? You're going to multiply it with 1 minus n, 1 over n minus 1, summation of xi's x bar, like this. It was this, like, right? You take the square differences from x bar. You first find the average of these things. You then take the average of all those, divide it by n minus 1. This is your sample variance. So sample variance, if you take the square root of this, this becomes your sample standard deviation. So using sample standard deviation, we can also again find what is the standard error of x bar. We are going to show the standard error, the standard deviation of x bar. Then we will be using this as an estimate for, this will be an estimate for standard deviation of x. Okay, so this is an estimate. So this is the actual parameter, this is the estimate, and we will be using this estimate to find the standard error. Okay, and it's the same formula basically. The only difference is that this is not given to us, therefore we need to compute it from the sample by using the sample variance like this. Is it clear? Oh, we use n minus 1 to make it an unbiased estimator. Otherwise, the expected value of, so in order to make the expected value of s square to be equal to sigma square, we need to divide it by n minus 1. Otherwise, the expected value of x squared would not be this. In order for this to be an unbiased estimator, we divide it by n minus 1. All right, all very good questions. Perfect. So let's continue with the hypothesis testing. So which is, as I said, the normal case. The H0 is called the null hypothesis, and there is an alternative hypothesis. And these are two mutually exclusive statements about some unknown parameter theta. And again, the section starts with some general parameter theta, but the entire, the hypothesis test we see in this chapter are going to be hypotheses about the means of populations, difference between means of populations, or proportions. So the same as confidence interval. We are going to be talking about mu's, proportions, and that's it, or differences between means or differences between proportions. So the unknown parameter will be the same. So we will be conducting z-tests and t-tests as we did. We conducted we constructed confidence intervals based on the z distribution, and we use the t distribution to construct confidence interval when the sample size is small and we don't know the population standard deviation. In that case, we use the t-test. The same here we are going to do. So in general, we collect data. So we take a sample, we compute a test statistic, and this test statistic, as I said, it was going to be either a z or t statistic. We'll be computing z-test or t-test. So this z will be standardizing. It will be about standardizing the sample mean that we collected by subtracting the assumed null hypothesis mean from it and dividing by the standard error of that x bar, or the sample mean that we have computed. And after this, by looking at that z value we have computed, we are going to say whether it's sufficiently different from this null distribution. What is if the probability that is coming from the null distribution is 0.95, for example, we are going to accept null hypothesis. If it's a level alpha, if alpha is 0.05, we're just going to reject H0 with 0. In the case where this collected statistic is in this 0.05 extreme regions of this null distribution. So we may take a look at examples, this 9.20. So I noted them as good examples to just how we state the hypothesis. It's not going to perform the actual test right now, but just these are examples that show how we conduct these tests, how we construct these hypotheses. 9.22, yeah. For example, this is the same example that I gave to verify that the average connection speed is 54 megabits per second. So this is a different hypothesis. So the internet service provider is not now claiming that it's more than 24 megabits per second, but the internet service provider is claiming that it is 24 megabits per second. Okay, now here, this is the claim of the internet service provider. The null hypothesis is this, and in this case, the extreme case, we are going to just say that no, you're lying. If you want to say to the internet service provider, no, you're not providing a service with 54 megabits per second, we need significant evidence that it is indeed smaller than that. Okay, we are not interested. If we do a test and it turns out that we have 80 megabits per second, are you going to complain about this? No. If you want to complain about it, you need to have significant evidence that it is smaller than 54 megabits per second. And having, for example, 53 megabits per second, again, is not very significant, right? If the internet service provider is claiming 54 and you get 53, are you going to tell them, no, you told me 54, it's 53, you're incorrect? You're not going to do that. So here, the alternative is it's different than 54 megabits. So this first alternative that is posed here is that as a mutually exclusive event. This is the normal case that the internet service provider is claiming. It's 54 megabits per second. It's an equality. So one thing that you should be careful about, this null hypothesis should always be an equality. And the main reason behind that is that we need to have a distribution that corresponds to the null hypothesis. All the acceptance and rejectance regions are done with respect to some distribution. And in order to have a distribution, specific distribution, this has to be set to some specific thing. For example, if the null hypothesis, we say that, okay, we call it mu is 54, but if you're okay that mu is 52 and 50 is between 52 and 55, for example, if you're okay with that, can we have a distribution, a normal distribution, which says that mu is between 52 and 55? No, right? I mean, the null distribution has a fixed, the normal distribution should have a fixed parameter. You cannot have multiple curves overlapping each other. The probability distribution itself is not fuzzy. It has a mean. It has to be a graph that is not blurry. It has to be fixed like this. Okay. In order to have such a fixed distribution, then we fix the null distribution to some normal case. The margin for the evidence is the alpha that we are going to see. Okay, so we are going to conduct hypothesis test with some level alpha. And you can choose that level alpha. We are, for example, here in this case, we are not actually conducting the test, but you may conduct hypothesis test, for example, at level 0.05 or at level 0.025. That alpha corresponds to the error that you may make, the probability of making an error in case, for example, it's actually 24 megabits per second, and you mistakenly say that it's smaller than that. So the margin for the evidence, that rejection region, is determined with the alpha parameter that you're going to specify to the test. So when we are conducting these hypothesis testing, we are going to say, we do this hypothesis test with alpha is equal to 0.05. This 0.05 determines our margin for the evidence. It will tell you, for example, you have to be smaller than this. So if you look at this test, for example, first it says that it's not equal to 54 here. Okay, the alternative is set like this. But as I said before, would we complain, for example, if it is 8 megabits per second? Probably no, right? I mean, we're looking for an evidence case here. This is the two-sided alternative. Two-sided alternative in which if it's significantly larger or significantly smaller than 54, we are going to reject the null hypothesis. But if you're just interested in the case where it's significantly smaller than 54, then we may conduct an alternative hypothesis that just states that it's less than 54. Okay, so this is how we if we have significant evidence, so the last sentence is good. If we only measure the amount of evidence supporting the one-sided alternative, we care about such evidences. If we have significant evidence that it is less than 54, we will say to the internet service provider, no, you're lying. It's not significantly lower than that. In the absence of such evidence, we will just gladly accept the internet service provider's claim. So if I drove this acceptance and rejection regions here, it's going to be something like this. So this is our null hypothesis distribution, okay, in which mu is at 54. Okay, it may have certain standard deviation. In this question, since we didn't conduct the test, the standard deviation was not given to us. But if you want to conduct really the test, we need to also know the standard deviation, because without not knowing the standard deviation, this curve can be like this, or it may be like this. We don't know how the curve is. Exactly. We will not complain when it's bigger. Exactly. If we have evidence, significant evidence that it's larger than 54, we would just not complain about it. So the alternative is something that we're looking for. If you're looking for something significantly smaller, then you conduct that. But in the case where the alternative, if we set this alternative hypothesis saying that mu is not equal to 54, and we conduct a level alpha test, what we're going to do is we are going to set the acceptance regions and rejection regions. By the way, this acceptance and rejection, the terms are for the null hypothesis. Okay, if you're accepting the null hypothesis or rejecting the null hypothesis. When we are conducting an alpha test, if it's a two-sided test like this side is going to be alpha over 2, and this side is going to be alpha over 2. This is the same as conducting a confidence interval around this with alpha, 1 minus alpha confidence level, right? I mean, this is we also at the same alpha here, the rejection regions where if the area is alpha over 2 both sides, that's a two-sided hypothesis test. But in our case, if we're conducting an alpha test and it's a one-tail test like this, you're only interested in the case where mu is significantly less than 54 megabits per second. In this case, the entire alpha is not going to be alpha over 2 like this. Level alpha test, one-sided level alpha test, we will want that 0.05 to be this entire left-hand side region. Okay. We may also conduct sometimes right tail tests, left tail tests, two-sided tests. It really depends on the semantics of what you're testing. Okay. So yeah, these are some two-sided, one-sided alternative examples here. So here is again verify the average number of concurrent users increased by 2000. So we are comparing two means. We can have hypotheses that test two means. The concurrent users before the upgrade, for example, concurrent users after the upgrade. If the claim is that it's increased more than 2000 after the upgrade, we may, again, our null hypothesis is some equality. The difference between them is 2000. Will be our equality hypothesis, and we will have for this one we will be able to again draw a specific distribution for the null hypothesis. And again, this is an inequality. If you're interested again in we may be interested in two different other alternative hypotheses as well. If we are interested in, for example, the concurrent user is increase less than 2000, we may have this alternative. Or if you're interested in an evidence which is more than 2000, we may have these alternative evidences. So here, so the last two sentences of this example actually tells us what these two different alternatives less than greater than mean. The test of null hypothesis against this first alternative less than 2000, it's evaluates to, you're looking for the amount of evidence that means the number of concurrent users changed by fewer than 2000. Okay, and here in all these cases, it's not written in this sentence here is that it's significantly fewer than 2000. Okay, we will not accept, for example, 1990 as fewer than 2000 because of our sampling error. If you get, for example, the difference, you get a sample and the difference turned out to be 1990. It's a smaller number than 2000, but can you claim that the new thing is less than 2000? It may be due to sampling error. This significantly, when we reject this null hypothesis and accept this alternative hypothesis, we just say that we should consider that we may make sampling errors even with the help of even in the presence of these sampling errors. If we see it's significantly lower, that significant difference tells us that the difference is probably not due to sampling error. It's probably that it's really decreased. Okay, but in all these cases, we may never for certain know that null hypothesis is true or alternative hypothesis is true. Okay, these are what we are conducting here, hypothesis test. It may always have errors because sampling, when we take a sample, it may have some errors. The sampling is not something 100% correct. We always have, we may have errors in our samples. Therefore, when we say that, we cannot say null hypothesis is true or null alternative hypothesis is false or true after the hypothesis test. We just say that according to our sample, we have significant evidence in favor of null hypothesis or in favor of the alternative hypothesis. Okay, the sample shows significant evidence. We can just say that. Oh, all these three examples, the first one was about means, this one is difference between means, and this example is about proportions. To verify if the proportion of defective products is at most 3%. So some companies claiming maybe this is a shipment, you will have defective products at most 3%. Again, if we want to tell that person, no, you're wrong, you have more defective products than that, we need significant evidence in our sample that the defective products is significantly more than 3%. So we conduct our hypothesis like this. Again, we will not complain it. I mean, the proportion of defective, when the company claims that the defect at most 3%, if we get 1% or 0% in our sample, this is still in the same this is the company's statement is still correct because they're saying at most 3%. So we need significant evidence that the defective products is more than 3% in order to accept the alternative hypothesis in favor of this one. Okay, so yeah, if the data suggests that the P is significantly lower than 3%, we will still be accept the shipment and we are not going to do anything. So now we come to different types of errors we can make in these hypothesis tests. And here, these type 1 and type 2, you may, it's really, I mean, this naming I don't like personally because these are just, they don't have any meaning, intuition in their names, just type 1, type 2. Or they could say error 1, error 2, or error A, error B. But the terms like false positive or false negative, these have more intuitive, I mean, they have some semantics in them. When you talk about a false positive, when you make an error like this, it will, the naming it as false positive is more meaningful. So here, what the type 1 error is the case where the normal case is actually the true case, but so this H1 is true, we never know this, but if H1 is actually true and you reject H0, if the null hypothesis is true and you reject the null hypothesis claiming that you have found a sample that shows you have significant evidence, you make type 1 error. So the type 1 error, the probability that we are going to make a type 1 error actually is the same amount of alpha. So when we conduct a level alpha test, we say that I accept to make type 1 errors with that probability, with probability alpha. Okay, because if you look at this, even in the normal case, even when mu is equal to 54, when the internet connection speed is 54, if it's normally distributed, when you take samples, it's still possible to get a sample in this range, right? So even when the internet service speed is really 54, and a number here is not still a member of this population. But if you limit this region to be equal to alpha, it means that a normal member of the population to be part of this extreme region is equal to alpha. You say that this is your type 1 error. Even if the internet service provider is right and in the population really is 54 megabits per second, you take a sample and it falls here, that probability is going to be, and you're going to reject the null hypothesis, saying that your internet service provider, you're lying, and you will be making this, you will be making an error actually if the H null hypothesis is actually true. If it's really true and if you reject it, you're making an error, a sampling error here. Due to your sampling error, you may get such results. And wrongfully rejecting null hypothesis is called type 1 error. And the type 1 error, as I said, an easier way to remember it is, I mean, it's the important parameter of this hypothesis test is this alpha when we conduct a level alpha hypothesis test. And 1 is the first error. Alpha is the important parameter. You can associate type 1 error with that alpha. Okay, so this is, you may also call this as false positive. In this case, the positives here, they correspond to your extreme cases, or it corresponds to the alternative hypothesis, where in which you're looking for things that are extreme. For example, you're looking for internet service providers that are lying. So your extreme case, for example, you're looking for a person who is sick, and this may be, for example, a COVID test in which the null distribution corresponds to the values that normal people get. Or yeah, we can also have some other example in which, for example, you're looking for cases where your vitamin D levels, okay, so the vitamin D levels of the normal population may be this, and if you conduct a test and want to claim that, okay, you have a test that shows whether a person has low vitamin D levels, okay, and uh, in this case, for example, you will be your null hypothesis is the vitamin D levels of the normal population. Even the normal population, as you can see, we can see vitamin D levels in these extreme regions. This is what the null hypothesis is showing us. But so when you conduct a test, your test is now trying to find, your test is going to be positive, saying that you have low vitamin D. Okay, so testing positive in some sickness test is not good, right? So I always remember a Seinfeld episode when I talk about this. When George Costanza, if you ever watched Seinfeld, so he makes a biopsy test for cancer. He's testing cancer, and on the phone, he's getting the test results, and the person on the phone is saying negative. Costanza starts crying. Negative, because negative is intuitively something bad, right? So he says negative, and then the person on the phone then tells him that no, negative is good. You don't have that, means you don't have the disease. So then he starts yelling, hey, negative is good, negative is good. So it's the same thing here. When we have a test for sickness, positive is that extreme case. And false positive means that you call a person sick wrongly. Okay, you call you're sick, but actually if that person's sample falls into this region, and you call him that you're sick, that will be and if that person is not really sick, then it will be a false positive. All right, so the false positive rate will be our alpha that we accept as. When we conduct a test with level alpha hypothesis test, we say that we may have a false positive rate of 0.01, and that's okay, or 0.05, whatever your alpha value is. The other error, type 2 error, which is after that I'm going to finish today's class. Type 2 error is the power of the test to find the real alternative. So it's here. When the alternative is actually true, so H0 is false, means that the alternative is true. When the person is sick and you told that person, no, you're not sick, you miss. So that's a false negative. You call that a negative. You're not sick. But if that person is really sick, that's a type 2 error. So avoiding type 2 errors is also called the power of the test. And and it is not shown in this graph here. We cannot have an area. So this area on the graph is alpha, which is our type 1 error. But since without knowing the distribution of the positive case, for example, what is the distribution of people with low vitamin D? If we also have such a distribution, let me change the color here. If somebody gives you a distribution that tells you this is the distribution of people with low vitamin D, okay, this is actually the distribution for our alternative hypothesis, but we don't have that. We don't have it in hypothesis test. This is just to show you an example. And sometimes in machine learning, we have the distribution of these two different cases at the same time. This is the distribution of H0, the null hypothesis. This is the distribution of the alternative hypothesis. We don't have this in hypothesis test. I don't want to confuse you by just showing this example, but just to make this power of the test to become clear. The power of the test, if your alpha is gets you this threshold on the null hypothesis, it also shows you that some of the alternative hypotheses here, people will have some high vitamin D here. Okay, so the area to the left hand side of this, so the level of your type 2 error will be the area under the curve to this right hand side. So you will be making errors, as you can see. If somebody actually who has a low vitamin D turns out to be have a vitamin D levels in this region of the x-axis, what we are doing is we are conducting our level alpha hypothesis test against this null distribution, which means that they are in the acceptance region. So we are going to accept the null hypothesis. So these people, we are if they're actually part of the alternative, they're actually part of the population with low vitamin D, we would wrongfully say that no, you have normal vitamin D. So that's a false negative, and the the the, pr- the probability to cover the alternative hypothesis, this area to the left hand side, is called the power of the test, which is the power to avoid false negatives. So these are two, as you can see, if I change this threshold to the right hand side, I can decrease the false negatives, right? If you take it here, false negatives will be decreased. But what are you doing in this case? You're increasing alpha, which means that you're increasing false positives. Your rejection region gets larger. So these two things, false negatives and false positives, they're always competing with each other. If you want to say, okay, I don't want to have false positives at all, I want to decrease this alpha. Decreasing the alpha now is going to also decrease. Decreasing the alpha means that you decrease your false positives. Now this time you're going to be increasing false negatives. So these two things are always, as I said, competing with each other in real life. In practice, what we usually do is we try to have tests with some fixed alpha. We want to fix our false positive rate to something, and we want to have tests with, we also want to minimize this false negatives. We choose a threshold in between them that's a compromise between these two things. I mean, in the extreme case, so I will stop the lecture after this example. In the extreme case, for example, I can have a COVID test with 0 false negatives. Okay, it's really easy. Whoever comes to your test, just say that you have COVID. Okay, if you tell everybody that they have COVID, you have a really nice test with great power. Okay, you're never missing a real COVID case. But what are you doing here? You're having lots of false positive. You will be telling people who don't have COVID you have COVID. Then it means that you're increasing the false positives. And the other extreme, where you have you don't have any false positives, you can say that everybody you don't have COVID, or you will never have. Or vice versa. I may have confused these things, but at the two extremes, you may have a test which always tells you you have that one, and the other case you don't have that one, and they will have full power and 0 false positive in either case, but they will be very bad test cases, because in one you will have a lot of false positives, in the other you will have a lot of false negatives. So a good test is a compromise in between these two, which you try to minimize both of them. All right, so that's it from me for today. We are going to continue with this and see how we conduct these tests And another thing we'll see is that, do we really need to fix this alpha to a fixed level? What if we, based on the value we compute, based on the value we get from the sample, we compute something we call p-value. This is what we are also going to do. Instead of having a fixed level alpha test, we will be computing a p-value, then make our conclusions based on whatever p-value we have, because it may be too close to call. If our z is close to this threshold, we may reject or accept depending on how where it is. So we will see these things on Thursday and hopefully finish chapter 9. All right. Have a nice day, everyone. I will see you all on Thursday.